Let's try doing some 3D animation, and fair warning, this will be more difficult than previous lessons. One way that we can do animation is we can have a 3D model, and specify the positions of the model's vertices at particular times. So for example, if we had a 2-second loop of animation, we could specify the positions of the vertices of a model at intervals of 1/5 of a second. So we'd have 10 different sets of positions. Then whenever we want to draw the model at a particular position in the animation, we'll actually be between two of those frames, two of those times. And in order to draw the model, we'll just interpolate between those two times. So we'll take a weighted average of all of the positions of the vertices. There are other ways that you can do animation. Skeletal animation comes to mind, which is more flexible, but we're just going to stick with this approach. So what I did is I went online to a website called blender.org, where I downloaded a program called Blender. It's a 3D modeling program, and it's free, open source, and that's what I used to make a 3D animation. So I'll just show you right here. This is the guy that I made using Blender. And so what I did is I just made him in Blender. He has one texture, which is right here, and it looks like that. And I'll just show you the finished project to show you what it looks like. It's just this guy walking forward forever on this floor right here. And in order to make this program right here, I took this right here, this Blender model that I made, and I exported it to MD2, the MD2 file format. The MD2 file format was used in Quake 2, which is pretty old, but there are a few reasons that we're going to be using it. One of them is that Blender is able to export to it. By the way, I'm using Blender rather than other programs such as 3ds Max and Maya, which professionals tend to use, just because Blender is free. And the MD2 exporter for Blender is actually pretty buggy right now, pretty temperamental. And I had to use an older version of Blender, version 2.42, in order to get it to export correctly. But hopefully in future versions of Blender they'll improve this. At any rate, there are a couple more reasons we're using the MD2 file format. One is that there are models available online that people have made for MD2. And another reason is that it's relatively easy to load in and to understand. So I just exported this to an MD2 file, and then right here in our program I made these source files right here, md2model.h and md2model.cpp, which take care of loading in the MD2 model and displaying the model once it's loaded in. So let's take a look right here. This is md2model.h. Our MD2 model is represented in this class right here, and it uses a few other structures up here. So it uses vertices, which have positions and normals, which are vec3f objects. It has frames, and each frame has a particular string representing its name, and it has a bunch of vertices, an array of vertices right here. And this array will be actually parallel in all of the frames. So for example, the vertex with index 2 will indicate the same part of the model in all the frames, but they'll still be in different positions because the model is moving around. Then we have this structure right here, which represents the texture coordinates of each of the vertices. And then we have a structure representing each of the triangles in our figure. Our figure is represented as triangles. And it does this using an array right here, which has indices of the different so it has indices into the vertices array right here, which stores the vertices at particular frames. And it also has indices into another array that we'll see for storing the texture coordinates of the different vertices in the model. Then we have the MD2 model class, which has an array of frames, has an array of texture coordinates, has an array of triangles. Then it has a variable right here for storing the ID of the texture of the model, which we saw earlier. Then it has indices indicating the starting frame and the ending frame for the particular animation we're on. because the MD2 file format can actually store multiple animations, which is done just using different ranges of frames. So, for example, our animation will range from frame number 40 to frame number 45, and that's what these two variables will do for us. Then we have this variable right here called time, which indicates the position in the animation. So a time of 0 will be the beginning of the animation, a time of 0.5 will be halfway through the animation, and a time of 1 will be the end of the animation. And it's a loop, so once it hits 1, it'll go back to 0 and start over. And this variable will always be between 0 and 1. Then we have the constructor for MD2 models. It's private because only a special method that we'll see later will be able to call it. We'll be able to construct MD2 model objects. Then we have the destructor. We have this function right here which sets the current animation. Because like I said, we can have multiple animations. We could have one for running, one for jumping. We could have lots of animations. And this will just set which animation we'll use, and we'll see how it works later on. Then we have this advanced function right here, which advances the state of the animation. So it basically just increments the time value. It increases the position that we are in the animation. Then we have the draw method right here, which draws the model in the appropriate position based on where we are in the animation. Then we have this function right here, which actually takes care of loading an MD2 model from a particular file. And it's a static method. You see the keyword right here, static. What that means is, in order to call it, we would type in MD2 model ::load and then the name of the file. And this call right here doesn't depend on already having an MD2 model object. So we're not calling this method on a particular MD2 model. We're just calling it. It's basically like a function, except that this is able to access all of the private methods and fields of an MD2 model object. So this right here is how we'll be able to load in an MD2 model. Now let's take a look at the Cpp file where all of these functions are actually implemented. And that's right here. First of all, we have this right here, this keyword namespace and an open brace, and then down later on, down here, we have a close brace for it. And this is just a special thing that we're doing for C++, and what it'll do is it'll make it so that we can have functions with different names in different files. So if we were to put a function called foo in this namespace block, we could also have a function called foo in main.cpp. So that's why we're putting namespace right here, so that we can have multiple functions or variables with the same name. Then we have this array right here, which stores all of the normals that the MD2 file format can have in it. So instead of specifying the normals directly, the MD2 file format has 162 predetermined normals, and you just specify an index into this array basically to indicate which normal you want to use. So here are all of the 162 different normals that are supported by the MD2 file format. And before we move on, I'd like to explain a little bit about Endianness. So when people were designing CPUs, there were actually a couple of choices that they had when they wanted to represent a number that used multiple bytes. So for example, a short number uses 2 bytes. And if we had the short 258, which is 1 times 256 plus 2, so it's the bytes 1 and 2, there are actually 2 ways that we could represent it. We could have the most significant byte first, in which case it would be 1, 2, in that order. Or we could have the least significant byte first, in which case it would be 2, 1, in that order. And if the least significant byte is first, it's called little endian, and if the most significant byte is first, it's called big endian. So when CPU designers were choosing between these two, actually some chose little endian and some chose big endian. So we basically have both kinds of endianness, which has been a source of annoyance for computer programmers since the dawn of time, or at least the last couple of decades. And I don't know, I think it's pretty stupid that we're using both of these endiannesses instead of just one to make things easier. But anyway, how does this affect us? Well, in the MD2 file format, there are multiple byte numbers. So it'll store shorts in the MD2 file format, and they're stored in little endian form. But the machine we're running this program on might not use little endian form. And we have to make sure that regardless of whether the machine we're running the program on is little endian or big endian, we'll still be able to load the model and everything will work just fine. So that's why we need this function right here, little endian, which figures out if we're on a little endian machine. So the way we do that is we have this value right here, short value, the number 1, and we just check the first byte of that value right here. If the first byte is 1, that means that we're using little endian, and if it's 0, that means we're using big endian. So that's how we figure out the endianness of the machine that we're on. So let me scroll down. We have these functions right here, toInt, toShort, and toUShort, which will convert arrays into integers, shorts, and unsigned shorts, which we'll have to do for reading in different things in the MD2 file format. So let's just take a look at the toInt function. Basically, it'll take each of the bytes of the 4-character array and then convert them into unsigned characters because we want them to range from 0 to 255. And then we use this bit shift operation right here. And what that does is it basically adds a bunch of zeros to the end of the binary representation of the number. So this right here, what it'll do is it'll take bytes 1 and it'll use the binary representation and put 8 zeros at the end of that. And then it'll take off the 8 bits that were at the front of that binary number. And basically this number, or this code right here, will convert a 4-character array into an integer, like we want it to do, if the 4-character array is represented as using little endian form. And this code right here will actually work regardless of whether we're on a little endian machine or a big endian machine. Then we have, it's the same idea for these toShort and toUShort methods. They operate in basically the same way. Then we have a method right here called toFloat. And turns out not even floating point numbers are immune from the little endian, big endian problem. So what we'll do for floats is we'll just have a variable right here called f. And then if the machine that we're on is little endian, then we'll set each of the bytes of f in the same order as the bytes array right here. So that's what these 4 lines are doing. If it's big endian, we just set them in the reverse order. And then we return the floating point value right here. So that's the toFloat method. Then we have a few methods right here that will actually read in variables. They'll read in numbers from an input stream, an IF stream. So right here we have a function that reads in an integer, and it does that just by reading in 4 bytes and then calling toInt on those bytes. So they make things nice and easy for reading in integers, shorts, and unsigned shorts from a file. And also we have one for floats right here. We also have one for reading in vectors, and it'll just read the next 3 floats in the input file, and it'll put it into a vec3f object. After that we have the load texture method, or load texture function, which we've seen before. It's been in previous projects. Then we have the destructor for the class, which will just delete all of the arrays in the class. Then we have a constructor, which doesn't do too much. Most of the action is in the load method right here. It just initializes some of these arrays to null and the time to 0. Then we have the load method, which actually loads in the model from a particular MD2 file. And we're going to see exactly how the MD2 file format works, how it's all structured in the file, as we read through this function right here. So first we just open the file, then we read in the first 4 characters, and the first 4 characters of every MD2 file are IDP2. So we're going to check to make sure that they're IDP2, and if they aren't, then we'll return null to indicate that there was a problem loading the file. Then the next 4 characters, or the next 4 bytes in the file, represent an integer, which is supposed to be 8, the version number of the MD2 file. So we just check to make sure that it's 8. So I'll scroll down. Then we read in a bunch of more information from the MD2 file. And all this stuff about the MD2 file format, I found it online, and I basically just wrote it into this program right here. So, for example, based on the file format, the next 4 bytes represent an integer, which is this texture width variable right here. Then we have the texture height, the number of bytes per frame, and a bunch of other stuff. It should be pretty evident based on the comments right here. And some of this information we don't need, like this right here, so we're not storing it in a variable. After that, we have these variables right here, which store basically the position of different data in the file. So for example, the texture coordinates are located at a particular offset in a particular number of bytes from the beginning of the file. And that's stored right here at the beginning of the file based on the MD2 file format. So we can just load it into this variable, and then later on we can seek to the appropriate position in the file. And again, we don't need all of these, so some of them we're just ignoring. So the first thing we're going to do is load in the texture. So we seek to the position where the texture information is stored, and then we read in the next 64 bytes, which according to the file format indicate a file name where the texture will be stored. So now we make sure that the texture is a bitmap file, because we don't know how to load in other kinds of file formats. If it isn't a bitmap, then we return null because we had a problem loading it. Then we load in the bitmap file into an image object. We turn it into an OpenGL texture, and then we delete the image object. We construct a new MD2 model object and set the texture ID field equal to the appropriate ID. Then we have right here, we're loading in all of the texture coordinates for the different vertices in the model. So the way that they're stored in the MD2 file format is each texture is represented as 2 short values. And so basically each texture will occupy 4 bytes, and we'll just read in the shorts using read short, and then we divide by texture width, which is up here. It's a variable that we loaded in up at the beginning. So that's how we can convert from the next 2 bytes in the file to the x value of the texture coordinate. Then we load in the y texture coordinate using the same approach, only we have to take 1 minus that coordinate, because the MD2 file format measures the texture coordinates from the top of the texture instead of from the bottom of the texture. That's why we need the 1 minus over here. Then we want to load in the triangles that we're going to draw. So we seek to the appropriate position, we create an array of triangles, and we set the num triangles field. So then we go through the file, and for each triangle there will be 12 bytes that represent 3 short values. The first 3 will be indices into an array of vertices, into the array of vertices that are stored in each of the frames. Then the next 3 will be indices into an array called text cores, which will have all of the texture coordinates. So this code right here takes care of loading in all the information about the triangles that we'll be drawing. Then we want to load in information about the frames. So we seek to the appropriate position again. We make an array of frames and set the num frames field, and then we go through each of the frames. So the first thing we'll do is we'll create an array of vertices that we'll use to store the vertices, and then each frame will be represented first of all by a scale and a translation vector. So we'll load these in by calling the readvec3f function, and we'll see what they do in a second. Then we load in the name of the frame, which is the next 16 bytes represented as a string, and then we go through all of the vertices in the frame and load them in. So each vertex is represented by 4 bytes. The first 3 bytes will indicate the position, and we'll treat each of these 3 bytes as an unsigned character and make them into a vector. And then to convert them to actual positions, we have to translate and scale them using the translation and scaling vectors. So right here we're scaling them, and then we're translating them. So we have the resulting position of the vertex that we're currently on. Then we read in another byte, and this byte will be an unsigned character, which will give us the index into the normals array that we saw earlier. So it'll specify which of the 162 predetermined normals will be used at that vertex. So right here, we figure out which index we're going to have, and then we store the normal for that particular index into the normal field of the vertex. And that's how we load in all the vertices for that particular frame. Then we just set up a couple more things on the model. We set the start frame and the end frame to particular values, and then we return the model that we've just loaded from an MD2 file. So that's how loading works, and that's how the MD2 file format is basically structured. Then we have this function right here, setAnimation, which we'll use to set which animation we're going to be working with. And it'll take care of setting start frame and end frame so that we're using the appropriate animation. Now we have to use the name field of each of the frames to figure out which frames are for that particular animation. So the name field of the frames will basically look like this. They'll start with the name of the frame, run for instance, or it could be jump, and then it'll have a number indicating which frame number it is in that animation. So we'll use this fact to figure out which frames are going to represent the appropriate animation based on the name that was passed to this function. So we'll just go through all of the frames, and then right here we'll check whether each frame, the name matches the name that was passed in as a parameter to this function. And based on that, we'll set the starting and the ending frames to be the appropriate values for the animation. So we'll have the correct range of frames that we want to draw. And that's the setAnimation function. Then we have the advance function, which advances the state of the animation by a particular fraction, and that just increases the time variable by the dt parameter. Then we want to decrease the time variable by its integer representation, which basically just chops off the integer part so that it's a fraction between 0 and 1. And we have this if statement right here in case the time variable gets to be really huge, in which case converting it to an integer we might run into problems. So if it's really huge, we just set it to 0 because it doesn't really matter too much. It's a rare occurrence anyway. So that's the advance function. Then we have the draw function, which is actually going to draw the model at a particular position in the animation. So first we enable textures, we specify the texture that we want to use, we specify the texture mapping, which is going to be the blurry texture mapping. Then we have to figure out the two frames between which we are. So right here we're going to figure out the indices of the frames that we're between. And we're going to have to average between these two frames to figure out where exactly all the vertices are in the model. So that's that code right there. This variable right here, frac, is going to be what portion we are between the two frames. So if frac is 0, that means we're at the first frame. If it's 1, that means we're at the second frame. And if it's 0.5, that means that we're halfway in between the two frames right here, frame 1 and frame 2. Then we call GLBegin GLTriangles to start drawing our triangles, and we iterate through all of the triangles. So for each triangle, we go through all of the vertices of the triangle, and we find out where the vertices are in each of the two frames right here. Then we take a weighted average of those two frames' positions and store it in this pose variable right here. We also take a weighted average of the normals of the two vertices. Actually, we're taking a linear average. There's a smarter way to take an average of two directions, but it's not that important. We don't care too much. It's actually more complicated to do the smarter average, so we'll just use a straightforward approach right here. Then we determine whether the normal vector is the 0 vector, because if it's a 0 vector, then it doesn't have a direction, and our normal vector has to have a direction. So if it's a 0 vector, we just set it to be this arbitrary vector right here so that it works. Then we call GL normal 3f using the appropriate vector. Then we figure out the texture coordinate. It's just an index into this text coords array, and we call GL text coord 2f. Finally, we call GL vertex 3f using the position variable that we computed earlier. And that's how we draw all of the triangles in the model. And that's the end of our md2model.cpp file. Now let's take a look at main.cpp, see how we use all of this functionality for loading MD2 files and drawing the models that are contained in them. So, first of all, we have this constant right here, which is just the size of each of the floor tiles. So, let me run the program. It's basically the number of units across each of these images, which in this case is 15 units. So that's this constant right here. Then we have the camera angle, we have the model object, we have the ID of the texture of the floor. Then we have the position of the guy. So it's basically how far he's walked forward, modulo the texture size of the floor. And that'll be used to make it look like the guy is moving forward. Then we have this cleanup method right here, which just deletes the model object. Scroll down. We have init rendering, which is going to call md2model : load in order to load in our md2 file. The md2 file is tallguy.md2, which is in the same directory as the source code. And then we make sure that the model isn't null, because if it's null, that means that there was a problem loading in the model. And we set the animation of the model to run. That's where I happen to put the animation that we're going to be using. Then we load in the floor texture right here, calling load BMP, load texture. And that's what we have in init rendering. Now let's go down to draw scene, where we draw the guy. So here it is right here. If the model isn't null, then we're going to do the appropriate translations, rotations, and scalings. And that's just because of the way that I happened to position this guy in Blender when I was making him. I didn't give him the correct rotation, scaling, and position. So we're going to rotate him so that he's facing in the appropriate direction, translate him so that his feet aren't sinking into the floor and he's not hovering above the floor. And then we're going to scale him so that he looks just about the right size. Then we call this draw method right here, which will draw the guy. Then right here we have where we're drawing the floor. And we translate downwards so that we're below the camera angle. And we set up our texture stuff for the floor right here. Then we're going to draw the floor actually as one giant quadrilateral that will range from -1000, -1000, to 1000, 1000. So it'll look like it goes on forever in every direction, more or less. And we draw it right here. We call GL normal 3f to set up the normal vector. And the way that we're going to make it look like the guy is moving forward is we're just going to set the texture coordinates as appropriate. So basically, the image will be moving along this quadrilateral. And we do that right here. We set the texture coordinates. And you'll notice that we're adding in the guy's position to figure out where to put the texture coordinates. So that's how we make it look like the guy is moving forward. And that's our draw scene function. In our update function, we have right here where we increase the angle to make it the camera spin around the guy. Then we have right here where we advance the animation by 0.025, which is the amount that we're going to be using. Then right here we increase the guy pose variable, which is used to determine how far forward the guy has walked. And this value right here, 0.08, I just figured it out by trial and error. It's basically the rate at which we want the guy to walk forward so that it looks like he's not sliding along the floor. Then we make sure that the guy pose variable lies between 0 and floor texture size. And that's our update function. And our main function, there's actually nothing new in that. And that's how we can do 3D animation in OpenGL.